Hi, I'm Elisha Jhoti, and I'll be speaking about my project with an extremely long title. I'd like to thank all of my collaborators that helped make this possible, and also the Barringer Family Fund for funding this project. Um, so, oh, okay, there we go. Awesome. Okay, so as most of us know, PSRs, or permanently shadowed regions, are regions on the moon that do not receive direct sunlight. And so we thought they would be very dark and so difficult for humans and rovers to operate in. However, Robert Wagner, in his LPSC abstract in 2024, used ShadowCam data to show that PSRs are not actually that dark. So Robert converted ShadowCam radiances to these measures called exposure values, or EVs. So EVs are a measure of how bright a human perceives a scene. And an increase of 1 EV represents a doubling of the amount of light in a scene. You can see in this picture on the left, this is from Robert's abstract. This is showing different levels of EVs like that you would come across inside a room in the indoors, ranging from like 6 or 7 EV with well lit rooms down to EV0, which is like pretty dark and you struggling to see things. This room is probably about EV6 for reference. EV14 is probably a clear day at noon with the sun directly overhead. The plot on the right is showing different EV values for some Artemis 3 candidate landing region PSRs. So we have Hayworth, Nobili Room 2, and a Floss crater, which is in the Mons Mouton landing region. The different colors represent different seasons, and the x-axis is local time of day on the moon. And so we can see already from this plot that there's a wide range of EV values in these PSRs. So some of them represent a well-lit indoor room. So it actually might be quite bright inside these PSRs. Ooh. Okay, so the aim of this project is to look at simulating South Pole lighting on Earth. So we want to simulate this kind of low angle lighting that we get at the South Pole for field training for our crew, testing rovers and navigational operations. So to do this, multiple analog deployments such as JET and Aardvark have used NASA's JSC artificial light source, which is this bright lamp that we see in this picture on the left. So Aardvark used rover and analog astronaut deployments to test nighttime augmented reality operations at Cinder Lake Crater Field. So thank you, Elise, for introducing that field site, because that is where I will be presenting this data from. So we had 2 lighting setups with Aardvark. We had the JSC lamps on the left, and then the right-hand picture is showing the Nevada National Security Site's LD8 lamp. So this is a very powerful bright lamp that's mounted on a truck bed. So I'll be showing data from both of these lighting setups. Sorry. Okay, so the aim of this project is to determine whether these Aardvark lighting setups accurately simulate South Pole lighting conditions by comparing to lunar data. So these pictures are showing some of the lighting conditions we had during Aardvark. So we had these really long shadows. You can see those in the bottom left-hand picture. This is, because the sun is always low in the sky at the South Pole. We have these grazing angles for sunlight. The craters in the field had very dark shadows inside them. And then you could really see small scale topography quite clearly. The top right image is showing some rover tracks. And you can see that contrast between the bright regions and the shadowed regions really brings out the small scale roughness. The bottom right image is an up-sun image. So you can see how bright these lamps looked at nighttime in the field, and they really wash out the rest of your surroundings. So that kind of gives you an idea of how bright the most extreme illuminated regions were. So to measure these field lighting levels, we use a light meter. So the one that we used was called the Gosen Lunar Pro. This is actually back from the 1970s, this light meter. It is still the best light meter for measuring dark conditions, and it's used by a lot of photographers doing nighttime photography. So it can measure an EV level down to -6, and that's where you really can't see anything with your human eyes down at -6 EV. So there are 2 types of measurements that you can take with this light meter. The first is using a diffusing sphere over the measurement window. So that is an instant light measurement. So that is basically measuring the light intensity that is falling on your subject that you're pointing the light meter at. The second type of measurement is a reflected light measurement, so that's without the diffuser, and that measures the brightness of your surface that you're pointing the light meter at within the field of view of the light meter. We did find that the orientation of the light meter to the source light significantly changed the measured EV levels, and that's because we do have quite a limited field of view with this meter. And I just say that there is a limitation to this project data because we're comparing oblique field-based images to orbital data. So you have very different sun angles when we're comparing to, orbital data sets from the moon. So a better comparison would maybe use some field-based drone data. But unfortunately, we don't have that yet. So we were just using our ground-based measurements. So here are some of our results from illuminated regions. So there's a lot going on in this plot. The bottom x-axis is local time of day on the moon for our lunar data. The lunar data are the yellow points and pink points. Yellow are LRO NAC images. So these are illuminated regions that are relatively flat, and they're about 12 eV, so pretty bright, like a well-lit summer day, noontime. And then the pink points are shadow cam data. So these are PSR points in the summertime, and the diamonds are the field data. So the green diamonds are from the LD8 lamp, so that's the super bright truck-based lamp, and then the blue diamonds are the JSC lamp. So you can see already that the LD8 is about the same level as a PSR on the moon in terms of brightness, and for these field data, we are using the top axis, that's the distance from the lamp. So we took these measurements stepping out every 10 meters in a straight line from our lamps. The JSC lamp, unfortunately, is not performing as well as the LD8. So it's really getting down into the lower levels of the EVs. And I've put a black dashed line at -6 EV. This represents the minimum detectability of the light meter. So if there is a point on that line, that means that it was too dark to take a measurement. So you can assume that it was either -6 EV or below that. So something that we want to think about with this project is the limits of human vision. So this red dashed line is the photopic vision limit. So that's where you're starting to lose color vision in your eyes, and you're no longer able to use both of your cones and rods at full capacity to see. So if you're going below this limit, then you start losing visual acuity and color vision. So this is important to remember. We also looked at shadows in the field. So this is looking at small scale shadows. So we took our light meter and we pointed it straight down at the ground inside some of these small scale shadows. And you can see a demonstration of that in the top right image. We did this with the JSC lamp, again, stepping out every 10 meters in a straight line, comparing it to some shadow cam data, which are the orange points. The JSC lamp immediately is too dark to take a measurement from about 10 meters onwards. So we're really pushing the photopic vision limit, and we're getting into mesopic vision, which is where you start losing full color vision. It's a transition vision stage, and you really can't see very well at this level of lighting. We took a measurement with the LDA when we were using that lighting setup of a shadow inside a crater, and that was also too dark to measure with our light meter. So overall, when we compare to human vision phases, we can look comparing the typical ambient light levels, so from like starlight to sunlight, that's shown in the top bar, and then the corresponding exposure values in pink, and then the range of our lunar south pole EVs, so our minimum PSRs were around -1, maximum illuminated regions are around 13, and then the field-based data have a much wider range, and the main problem that we see here is our minimum shadowed regions are in the scotopic phase of human vision. And that is where you lose your color vision, you have very poor acuity, and it takes your eyes a long time to adjust to this phase of human vision. So the key takeaways from this project are that you had to be very close to the light source to match the same level of brightness as lunar illuminated regions. We have a wider range of EV values in the field compared to on the moon. And our shadows in the field are too dark. We're in the scotopic vision range, and that means our eyes take 30 minutes to fully adjust, which would be all right if we stayed in the shadows, but we're switching between illuminated regions and shadows, so our eyes are switching between mesopic and scotopic vision, which is very difficult for our eyes to do, and it will really affect your visual acuity. So overall, human navigation operations in shadow terrain with these lighting setups is more challenging compared to the lunar surface. And that's the end of my talk. Thank you so much.